Hello, good morning to today's class. We stopped at permeability in the last class. Today we are moving on to discussing logs, their interpretation and uses. Now, the first log we're discussing is SP log, called spontaneous potential log. And this log is used primarily to detect permeable beds and to locate their boundaries and permit correlation between wells. In the oil industry, the SP log is what they use to differentiate sand and shale, and they call it a lithology log. As a matter of fact, it's called lithologic indicator. It's also used as a qualitative indicator of bed shaleness, and used to determine the shaleness of bed when they are calculating the shaleness of beds. It can also be used in the determination of the resistivity of formation water. It's applicable there. It consists of a galvanometer, a shelf, a neutral point, and the measuring point downhole. Usually as a result of passage of current. Now, there are factors necessary for the generation of SP currents. We have the conductivity of the fluid in the borehole. And you know, there are two types of fluid in the borehole, the water and the, the hydrocarbon. Now, the water is conductive and the hydrocarbon is non-conductive. Also, a porous and permeable bed surrounded by an impermeable formation. A porous and permeable bed surrounded by impermeable formation. So, then the third one is the salinity differential between the borehole fluids and formation water. The salinity differential between the borehole fluids. All these three combine together to generate SP current that is measured in SP log, in downhole log. Sources of SP. SP current originate principally through electrochemical effects of salinity difference between borehole fluids, which is primarily mud filtrate, and the formation water. It generates electrochemical potential because there is a differential between them. One is mud filtrate and the other one is formation water, the virgin formation water. These different create spontaneous current in two ways. One of which is when the fluid which is mud filtrate or mud plus formation water, themselves come in contact through a porous medium. A porous medium. And then the second one, which is called the diffusion potential. That one, the first one is called diffusion potential. Then the other one is when they came in contact through a shell, which acts as a semi-permeable membrane. And because it's a shell, it's called a shell potential. The point of contact is shell. The diffusion potential is about 70% of SP. The shell potential is about 83%. So the combining potential from 100%. The actual SP current are measured in borehole. Are largely the result of combination of the two electrochemical potential. Oleochemical effect. If you consider a porous and permeable sandstone penetrated by a borehole, the moon filtrate is less thinner than the formation water. You know, if you drain in marine environment, the formation water is saline, and a brine solution will conduct electricity. Opposite the sandstone bed, the less saline solution, that is the moon filtrate, will become negatively charged as a result of the diffusion potential. But above the sand, opposite the shale, that is semi-permeable membrane, that is semi-permeable. Because of the shear potential, the less saline solution will become negatively charged. Positively charged, rather. The less saline solution will become positively charged, while the saline solution will be negatively charged. As a result of the diffusion potential. The excess charge is therefore sand and positive opposite the shale, as you can see in the diagram. Across the shale, therefore, there is an inflection between the boundary separating shale and sand. And current move from diffusion potential to shale potential because diffusion potential is negatively charged. And current will move from negative to positive. Then, at the point of contact between the permeable sand and the shale, there will be an inflection point, as you see in the diagram, which will indicate which will separate the two. And that is why the SP log is good in lithological indicator. The couple work in complementary sense and create a spontaneous current flowing through the borehole, the porous formation, and the contiguous shale. It's like a couple system. Note, the flow of current is focused at the bed junction. It is only here that there is a change in potential. This is very important because SP current permits not absolute values, but changes in values which occurs at bed junction only. If a bed is impermeable, ion will not be able to move, and hence there will be no current. If a bed is impermeable, ion will not be able to move. Like this membrane polarization in IP. Because they are porous, but they are not interconnected. So there won't be room for the current to actually pass through those pores. But because it's negatively charged, it will be a charge but no current flow. Hence, there will be no current flow. And no potential changes, that is no SP. However, if the slightest permeable, however, even the slightest permeability will permit current flow and SP will be recorded. So permeability, in other words, support SP flow, current flow, and SP generation. In a clean and permeable in a clear and permeable medium, that is non-shaly condition, clear and permeable, non-shaly condition, will be essentially sand. The total electrochemical effect corresponding to two phenomena above, diversion and shale is given as EC is equals to minus K log A subscript W over A subscript MF, where AW and AMF are the chemical activities of moon water and moon filtrate, respectively. K is the constant and K is the constant and roughly proportional to absolute temperature. But the resistivity of the solution that is conducted is roughly proportional to the reciprocal of its activities at low soil concentration. And therefore, RMF is proportional to 1 all over AMF. A subscript MF. R subscript MF is proportional to 1 all over A subscript MF, which means the resistivity of moon filtrate is proportional to 1 all over chemical activities of moon filtrate. Therefore, RMF all over RW is equals to AW all over AMF. That is EC, which is electrochemical action or current, is equal to SP, and is equals to minus K log RMF all over RW. Where K is equals to T plus 505 all over if. Then you now have RW from SP log. So you can substitute that into the equation. Now, resistivity of water from SP log. Another subtitle. The SP log can be interpreted both qualitatively and quantitatively. One qualitative use is the RW determination. Recall the relationship among SP, RMF, and RW. SP is equals to, which is EC. EC, electrochemical action, is the spontaneous potential, which is equal to minus K. We have defined K to be is equals to T plus 505 all over 8. Is a function of temperature. Minus K log RMF all over RW. And its unit of measurement is in millivolts. K is usually constant. And if you look at the diagram, you see that SP is graded between 0 and minus 150. You now have shape baseline. And it's usually placed at the first end in correlation. The first one in track 1 is always in track 1 in a composite. Then you now have track 2 conductivity log and resistivity log. Then track 3 sonic, neutron, and density log. By expression, one can determine RW knowing SP, K, and RMF. You can determine RW from those equations. SP can be read in a clean and thick water-bearing cell. K, which is equal to T plus 505 over 8, is the formation temperature in degree Fahrenheit. Although it can be converted to degrees centigrade. The surface value of RMF can be determined in the laboratory. All these anomalies enter into log reading. In case no value of RMF is given, but RW is given, we can determine RMF from a chart. Assuming I provided all those and I ask you to determine RMF, and I provide for you a residue of water chart, I'm sure you'll be able to determine that. At high salt concentration, resistivity no longer inversely proportional to the activity, to the chemical action, activity of chemical action. In this case, we define the effective or equivalent resistivity, which we call RWE, which are inversely proportional to the activity, this chemical activity. So RWE is equal to 0.075 all over RW at a particular temperature, say it's 77 degrees Fahrenheit. So RWE is equal to 1 all over AW. And equation becomes EC or SP is equal to minus K log into bracket RMFE all over RWE. Step 1. Establish the formation temperature given surface and bottom hole temperature. One can extrapolate the surface temperature. Where T formation is equal to T SUF plus depth times TG. TG is temperature gradient, and you can always find them in a chart. Then there's an example already given here, which have been worked out. They are given a borehole temperature of 200 degrees Fahrenheit and a depth of 11,305 feet. And this surface, temperature of the surface, is equal to 70 Fahrenheit. Then find the temperature gradient in degree Fahrenheit at 100 feet. Also, find the formation temperature A at 9,565 feet. Answer 1.15 at degree Fahrenheit per 100 feet. And 179.9, approximately 180 at the depth stated above. Or the question has been worked out. Step 2, conversion of RME to RMF at formation temperature. you can use the ARMS formula, which is equal to RT is equal to T1 plus 7 into R1 all over T2 plus 7. Example given as well, which I worked out.